Welcome to Tomorrow Unveiled, the program designed to get you completely up to speed on the most foundational and pivotal shifts happening in technology without ever feeling overwhelmed by the data overload.
Yeah, and this week, it feels like the narrative around artificial intelligence didn't just inch forward. It really accelerated past a kind of tipping point.
A tipping point, how so?
Well, we're not just talking about models getting slightly larger, or a bit faster anymore. What we're seeing now is more like a fundamental unveiling of entirely new paradigms,
Okay.
new ways of thinking, specialized hardware architectures, and, well, groundbreaking applications that are actually solving problems scientists have wrestled with for like a century. The focus, it's really shifted from just scaling up incrementally to specialized novelty.
That's a huge claim. Fundamental novelty over incremental scaling. So let's unpack this. Our dedicated research team, they've compiled a stack of cross-corroborated reports really digging into this, and they've identified three massive converging themes that defined this specific week, October 13th to 20th, 2025. This feels like the blueprint of the future delivered right to you.
Right. The first pillar is this transformation of AI into, well, a true scientific collaborator.
Yeah.
We're moving beyond just data analysis. We're talking about what we're calling generative science.
Generative science.
Yeah, where AI partners with humans to create genuinely novel, verifiable hypotheses. And foundational fields like medicine, like physics, it's not just crunching numbers, it's generating ideas.
Okay, that's pillar one. What's the second?
The second pillar really defines the battleground for this new era, the great hardware fracture.
Hardware fracture.
Exactly. The old general-purpose GPU monopoly. It's crumbling. We're tracking the emergence of four quite distinct, specialized silicon ecosystems, each one optimized for a specific slice of the AI economy.
Four different ecosystems. Interesting. And the third pillar.
And finally, pillar three. We have to confront the reality of maturing challenges.
Ah, the downsides.
Well, yeah, or maybe the complexities. As the technology grows, so do its quantifiable systemic costs. We need to look at the second-order societal effects, things related to our long-term cognitive impact, legal accountability, especially in high-stakes areas, and frankly, the sheer sustainability challenge of running AI at, like, gigawatt scale.
You're right. So our mission here on Tomorrow Unveiled is to give you that clear, organized shortcut to really help you understand these pivotal shifts and equip you with the memorable details, the context. Because the future isn't some vague concept, is it? It's being built, like, right now.
Absolutely. It's happening fast.
Okay, let's jump into that first shift then, the one that sounds most, maybe, intellectually thrilling. Generative science. We've used AI for analysis for ages, right? Recognizing patterns, making predictions based on old models. But the reports from our research team, they confirm AI is now becoming a genuine originator. It's generating novel hypotheses that lead to real, testable breakthroughs.
Yeah, well, what's really fascinating here is that the first, maybe the most striking flashpoint for this shift is in biomedicine. Specifically in the extremely difficult area of cancer immunotherapy.
Immunotherapy.
Yeah, this is an area where, traditional human-led hypothesis generation, it's been slow, incredibly costly.
Okay, so what's the tech breakthrough here? The reports mention a model called Zell 2-sentence scale 27B, C2S scale 27B, built on the Gemma family. Can you walk us through that? Why Zell 2-sentence? What's the significance?
Well, the analogy is pretty clever, actually, because it really captures the function. Think about how a large language model learns grammar, meaning in human text. The C2S scale 27B model is engineered basically to understand the language of cells. It processes incredibly complex single-cell data, transcriptomics, proteomics, morphology, you name it. Essentially, the full biological state of millions of cells. And it organizes all that into meaningful, machine-readable sentences.
So it's translating biology into a kind of computational syntax.
Exactly, which allows it to reason across different biological contexts in a way humans will struggle to.
And what specific, potentially life-altering challenge did this model tackle?
The big one was how to effectively treat cold tumors. This is a huge bottleneck in cancer immunotherapy.
Cold tumors, those are the ones the immune system ignores, right?
Precisely. They fail to get a significant immune response. They're basically invisible to the body's T cells, which means drugs designed to boost the immune attack, like checkpoint inhibitors, they just don't work effectively. So researchers desperately needed a way to turn those cold tumors hot, to make them visible to the immune system.
That sounds like a ridiculously complex search space. You're not just looking for one drug. You need like a specific trigger, maybe under certain conditions.
Exactly. A complex conditional trigger that changes the tumor's whole biological state. And this is where the AI approach was different.
How so?
It didn't just search based on, existing human assumptions or known pathways. The AI performed this really sophisticated dual context virtual screen.
Dual context.
Yeah, across a library of over 4,000 existing small molecule drugs. The dual context part is crucial. It wasn't just asking, does drug A affect cell B? It was asking, does drug A, only when context C is present, like specific immune markers, affect how the cell presents tumor antigens.
Ah, so it's looking for conditional effects. And that leads us to the really memorable detail, the thing that shows the AI was thinking non-linearly. What did it predict?
So the C2S scale 27B model proposed this novel, actually quite counterintuitive solution. It predicted that a specific drug, silmutecertib, would dramatically boost antigen presentation. The immune signaling that makes a tumor hot, but only when it was given together with low levels of interferon.
Interferon, that's a common immune protein, but only low levels.
Exactly, low levels. This specific conditional requirement, it wasn't obvious at all from existing literature. It was a genuinely generative hypothesis, derived solely from the model's deep understanding of that cellular language.
That's the real milestone, isn't it? It's not just finding patterns in known data. It's connecting three previously separate pieces: the cold tumor state, this drug silmutecertib, and low-level interferon into a completely new, testable therapeutic idea.
Absolutely. And the significance, well, it was cemented almost immediately by validation. Subsequent lab experiments, using human neuroendocrine cell models, they showed roughly a 50% increase in antigen presentation when these exact elements were combined.
Wow.
Yeah. This successful, really rapid transition from a pure in silico prediction, a computer model, to measurable in vitro validation in a lab. It fundamentally redefines AI's role. It's not just an assistant anymore. It's more like a co-investigator,
Right.
capable of leading those initial critical steps of discovery.
That is profound, truly profound,
Yeah.
demonstrating AI accelerating human ingenuity right where we need it most. But our research team also highlights this acceleration isn't just in biology, right? It's starting to remake foundational science everywhere. Physics, for instance.
Yeah, that brings us to a really complementary breakthrough, detailed and corroborating reports from Los Alamos National Laboratory. It concerns a framework they call Theathor.
VR, like the god of thunder.
Huh, maybe. This AI solution effectively cracked a computational problem in materials science that had basically stumped traditional approaches for nearly a century.
A century-old problem. That suggests the old methods weren't just slow, they were maybe fundamentally inadequate. Was Store just throwing more computer power at it, or did it do something fundamentally new?
It really introduced a new computational technique to manage the complexity, the combinatorial explosion problem, they often call it.
Right.
In materials science, if you want to simulate something like copper accurately, you have to track the quantum behavior of millions, maybe billions of atoms all at once. And when you try to model defects or impurities or unique states, the number of variables just multiplies exponentially. It becomes this intractably high-dimensional problem that even conventional supercomputers just hit a wall on.
So if the problem space is exponentially bigger than the available compute, how did Thor break through that ceiling?
So Thor uses this complex mathematical technique. It's called Tensor-Train cross-interpolation. Now, simply put, what it does is identify the essential correlations, the really important patterns within that massive sea of data, and it filters out the non-essential noise. It transforms the high-dimensional problem into a much lower, more manageable dimension.
Okay, so it's not ignoring the complexity, it's finding a smarter, more efficient way to represent it.
Exactly. It finds the optimal way to represent it efficiently.
And the practical result, the payoff for that efficiency.
Well, when they used it to reproduce high-fidelity simulations for materials like copper, Theor did the required work over 400 times faster than the previous state-of-the-art computational methods.
400 times faster.
Yeah, and, to put 400x speed in context,
Yeah.
a calculation that might have previously tied up a dedicated supercomputer for, say, half a year, now it can be done in less than 2 days.
That's game-changing.
It totally changes the entire product development cycle, materials discovery,
Yeah.
think batteries, superconductors, alloys, everything.
Incredible acceleration. And finally, on this generative science theme, the research notes confirm AI is even generating algorithms now, breaking established mathematical limits.
Yes, exactly. Systems like AlphaVolve, which was deployed by Google DeepMind, are clear evidence that AI is now capable of auto-generating, evaluating, and even optimizing its own fundamental algorithms. It's essentially AI acting as a coder for the AI infrastructure itself.
And the result our research team highlighted was breaking a 56-year-old mathematical record in a core area like matrix multiplication.
Precisely. Matrix multiplication sounds academic, but it's absolutely fundamental to almost everything in modern computing. Graphics, simulations, and especially large language models. The new algorithm, discovered autonomously by AlphaVolve, it achieved a small but critically important improvement in efficiency.
And even a small improvement matters at scale.
Right. Hugely. Because this algorithm was then deployed to optimize Google's core infrastructure, which runs on hundreds of thousands of GPUs globally. That small optimization actually recovered a significant percentage of their global compute resources. That's immediate, tangible benefit. And frankly, it's environmentally friendly, too, getting more work done with the same hardware, all derived from AI-generated math.
So yeah, generative science is definitely happening. AI generating potential cures, optimizing physics simulations 400 times faster, and even writing the underlying code for its own efficiency. That really fits the unveiling narrative you mentioned.
It absolutely does.
Okay, so this incredible computational demand, especially for the kind of high-speed, iterative work that generative science needs, it must put enormous strain on the existing infrastructure, right? If AI is solving these massive new problems at this pace, we have to ask, where is all this intense computation actually happening?
And that brings us perfectly to the second massive theme our research team flagged this week, the great hardware fracture. The industry consensus is clear now. The era of the general-purpose, one-size-fits-all GPU, it's basically over.
Over? Why?
Well, economics and just basic physics dictate specialization is needed now. The market is visibly fracturing into, as we counted, 4 distinct hardware ecosystems, each one optimized for very different needs.
4 niches. Okay, what are they?
You've got on-device performance, then frontier training at massive scale, open data centers, and finally, inference efficiency.
That makes sense. I mean, the requirements for training a massive 27 billion parameter model are totally different from just running that model on your phone or laptop.
Completely.
Okay, let's start with niche one then. On-device, distributed AI. The example highlighted is the new Apple M5 chip. This looks like Apple making a big play for edge AI supremacy.
Definitely. The M5 chip, it's built on their third-generation 3-nanometer technology, but the key thing is an architectural shift. Previous Apple chips had, a centralized neural engine.
Right.
The M5 architecture is different. It embeds dedicated neural accelerators directly into each individual GPU core. So it's spreading the AI intelligence across a highly parallel distributed fabric within the chip itself.
What does that distributed approach actually achieve that the old centralized engine couldn't? And why is that the key for localized processing?
Well, a centralized engine inevitably creates a bottleneck, right?
Yeah.
Every AI task has to queue up for that single resource. By distributing the intelligence, the M5 achieves true concurrency. It allows the chip to run quite complex models, think specialized LLMs or advanced diffusion models for image generation, right there on the device.
On the new MacBook Pros, the Vision Pro.
Exactly, without constantly relying on the cloud for every little step. And the performance numbers are significant. This design delivers over 4 times the peak AI compute performance compared to its predecessor, the M4. But crucially, it's optimized for power-efficient, real-time, localized processing.
Power efficiency is key for mobile.
Absolutely. You can't afford to have a laptop or, worse, a VR headset overheating constantly. So Apple's focus is clear: efficiency and locality for the consumer edge.
Okay, so Apple's doubling down on the edge. Let's pivot completely to the other extreme. Niche 2, frontier training and custom silicon. This sounds like it's all about achieving maximum speed at absolutely astronomical scale. And the big players here are OpenAI and Broadcom.
Yeah, this partnership, it signals a really high-stakes strategic move. It's about achieving full-stack control. Instead of just buying off-the-shelf components, OpenAI has formally jumped into the custom chip design game.
Designing their own chips.
Well, co-developing them with Broadcom. They're creating custom AI accelerators tailored specifically to the unique, probably proprietary requirements of their next-generation frontier models, whatever those might be.
And the scale of this commitment is just mind-boggling. Our research notes mention 10 gigawatts of custom capacity, planned for rollout between 2026 and 2029. I mean, 10 gigawatts isn't just a big data center. That's approaching the power draw of entire cities.
Yeah, the scale absolutely confirms that securing and, importantly, controlling the specialized compute infrastructure is now the primary determinant of AI leadership. It's non-negotiable at the frontier, but the technical risk they're taking is equally immense.
How so?
It's their massive bet on the network. They plan to use Broadcom's standard Ethernet networking solutions to connect all these custom chips together.
Why is using Ethernet a bet? Isn't Ethernet everywhere?
It is ubiquitous, yes, but it directly challenges the proprietary high-performance fabrics, things like NVIDIA's InfiniBand, that currently dominate every single existing large-scale AI cluster.
Okay. Why do those fabrics dominate?
Because those proprietary fabrics, while expensive and closed, offer extremely low latency, which is absolutely essential for ensuring that thousands, maybe tens of thousands of GPUs can communicate almost instantaneously during those massive month-long training runs.
Right, so OpenAI and Broadcom are betting against that.
They seem to be banking on Ethernet scalability and, frankly, lower cost, eventually overwhelming InfiniBand's low latency advantage. They're aiming for vertical integration, optimizing the chip, the memory, the network, the whole stack for massive throughput, even if it means sacrificing maybe a tiny bit of that ultra-low latency. It's a calculated, potentially industry-disrupting risk, all aimed at long-term efficiency and, crucially, full control over their stack.
Okay, so if OpenAI is betting on a closed, vertically integrated stack, Niche 3 sounds like the complete opposite. Open data center infrastructure led by Meta and AMD.
Absolutely. It's a direct philosophical counterpoint. Meta introduced something called the Open Rack Wide Standard, or ORW. It's basically an open-source blueprint for the physical rack itself, optimized for hyperscale. AI needs better cooling, power delivery, standardized dimensions. It's an attempt to commoditize the very building blocks of the AI data center.
Making the infrastructure less proprietary.
Exactly. And AMD immediately jumped in to support this by unveiling their Helios rack-scale platform.
What's the significance of Helios?
Helios is the first complete system blueprint built entirely on that open ORW standard. It showcases AMD GPUs, their ePYC CPUs, and crucially, open networking standards. The message is simple. Here's an open blueprint designed specifically to foster interoperability.
To avoid vendor lock-in.
Precisely. The joint goal of Meta and AMD seems to be preventing the kind of vendor lock-in that proprietary systems inevitably create. They want to make the underlying infrastructure more of a commodity, which theoretically shifts the competitive focus back to the actual performance and efficiency of the silicon, the chips themselves, and the models, rather than who controls the exclusive data center design.
Interesting strategic maneuvering. Okay, that brings us to the fourth niche, the inference economy, driven by Intel's Crescent Island data center GPU. This sounds like an adaptation born purely from economic necessity.
Yeah, this is perhaps the most economically shrewd specialization we're seeing. Our research confirms a major industry trend. The total cost of inference just running the already trained models day to day is projected to soon dominate the massive cost of training them in the first place.
So running the AI costs more than building it, eventually.
Over the lifetime, yes. And Intel's Crescent Island GPU is optimized explicitly for this inference workload. They're consciously sacrificing some peak training performance for sheer energy efficiency and a better scientific efficient. Total cost of ownership, or TCO.
How exactly did they design for TCO? What were the specific trade-offs they made compared to, say, a frontier training chip like OpenAI might be building?
Well, they made very deliberate choices, especially around memory. Training chips typically rely on extremely expensive high-power HBM high-bandwidth memory to handle the immense simultaneous data flow needed during those big training cycles.
Right.
Crescent Island, however, uses a very large amount, 160 gigabytes of lower-power LPDDR5X memory.
LPDDR5X, like in phones and laptops.
Exactly. It still offers excellent bandwidth, plenty for inference tasks, but at a dramatically lower cost and, crucially, much lower power consumption per gigabyte. Furthermore, the whole design is optimized for traditional air-cooled servers. They're intentionally avoiding the complexity, the huge capital expense, and the long-term operating costs associated with the liquid-cooled racks that frontier training often demands.
So it's all about minimizing that long-term operational expense, the cost of running billions of queries or tasks every single day.
Exactly. And this focus on continuous cost-efficient inference power, it directly addresses the booming enterprise demand for something called Agentic AI Systems, which our research team also highlighted this week.
Agentic AI, can you explain that? And why is it the perfect customer for a chip like Crescent Island?
Sure, Agentic AI refers to these more autonomous systems. They're designed to perform complex, multi-step tasks. Think of a system that, say, reads an incoming customer email, checks inventory in a database, drafts a proposed order confirmation, and then routes it for human approval.
So it's not just one query, it's a sequence of actions.
Precisely. Unlike a single query to a big language model, these agents require continuous calculation, often hundreds of sequential low-latency calculations just to complete their internal planning loops and execute the multi-step action. They aren't training, they are inferring over and over and over again very rapidly. This sustained high-volume inference absolutely demands extreme cost and power efficiency. And the business cases there, reports are showing these agents are already doing things like reducing contract execution time by 65% in some enterprises. That generates serious ROI, which in turn demands this kind of specialized, inference-optimized silicon.
This convergence of specialization is fascinating. It really makes you wonder who wins the long game. We are witnessing the future being built in real time, fragmented into these highly optimized niches. Here's where it gets really interesting. We are witnessing the future being built in real time. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
Yeah, it's a fundamental shift in the landscape.
Mm.
So while the technological unveiling we've just discussed, from the generative science breakthroughs to this great hardware fracture, is genuinely exhilarating, the discourse around AI seems to be maturing right alongside the tech itself.
Maturing how?
Well, the industry and society really seems to be moving past just abstract philosophical ethics discussions. We're starting to confront quantifiable systemic challenges that are manifesting as second-order effects, real-world consequences.
Okay, let's start with maybe the most personal and potentially concerning effect, the neurological frontier, this concept of cognitive debt. If AI is doing more of our thinking for us, is that actually impacting our physical brains?
That is the absolutely central question raised by a pretty high-impact study that our research team highlighted. It used EEG data, measuring brain waves, to provide actual neurological evidence of the cognitive impact of relying heavily on generative AI tools.
How did they test that?
The methodology was fairly straightforward. They compared the brain activity of participants doing complex tasks like writing essays. One group used AI assistance heavily, another used traditional tools like spell checkers, and a third group used no assistance.
And what did the EEG data show? What was happening in the brains of the people leaning on AI?
Well, the findings were quite specific and frankly a bit alarming.
Yeah.
The participants who relied heavily on generative AI for their writing exhibited weaker neural coupling.
Weaker neural coupling.
Yeah, and what they describe is a systematic scaling down of brain connectivity compared to the other groups. And crucially, this reduction in connectivity, it was observed specifically in the areas of the brain we associate with things like sustained attention, critical thinking, creative synthesis, fundamental cognitive processing, largely within the prefrontal and parietal cortices.
So the brain is quite literally not working as hard? In the areas required for deep original thought, resulting in this cognitive debt. It sounds like maybe we're trading short-term convenience for potentially the long-term erosion of our core mental abilities.
That is precisely the term the researchers coined, cognitive debt. I mean, the brain is optimized for efficiency, right? If a tool consistently provides the answer or does the heavy lifting without requiring the user to really engage in that difficult work, generating hypotheses, complex synthesis, then the neural pathways required for that effort.
Well, they might begin to atrophy over time.
Use it or lose it, basically.
Kind of. It shifts the ethical debate, doesn't it? From just external harms like algorithmic bias to these intrinsic neurological consequences for the user themselves. It raises profound questions for education policy, for lifelong learning.
Yeah, absolutely. That's a quantifiable physiological concern.
Oh.
Okay, moving from the personal to the systemic. The massive second-order effect our research highlights is this growing legal vacuum, especially in high-stakes domains like healthcare, where, as you mentioned, generative science models like C2S Scale 27B are starting to generate life-altering medical hypotheses. Exactly. As AI gets integrated more deeply into critical clinical environments, legal experts are definitely sounding the alarm. They're warning about an escalating blame game, or perhaps more accurately, an accountability vacuum, when medical errors might be caused or influenced by algorithmic recommendations.
An accountability vacuum.
Yeah. The central problem is the sheer difficulty, maybe even an impossibility sometimes, of establishing legal fault when a negative patient outcome occurs, and an AI's output was involved in the decision-making process.
So if an AI suggests a diagnosis or maybe a treatment path that ultimately leads to patient harm, how does a patient or their family or even the hospital seek legal recourse? What are the roadblocks?
Well, the barriers are pretty formidable. It mainly revolves around the proprietary nature of the technology, the classic black box problem. First, just establishing a direct, legally provable causal link between a complex algorithm's specific output and the resulting harm. That's incredibly tenuous legally. Second, getting access to the proprietary source code, the training data, the weighting, everything you'd need to actually prove negligence or a fundamental design flaw. That's nearly impossible because of intellectual property protections.
Companies aren't just going to hand over their secret sauce.
Not likely.
Uh.
And third, even if you somehow got access, proving that a standard of care was breached often requires proposing an alternative, safer algorithm design, which realistically very few people outside the company that built the AI could actually do.
The legal system just wasn't built for this, was it? For a non-human, non-transparent entity making potentially life or death recommendations.
Exactly. And the paradox here is serious. This lack of clear liability frameworks, it creates tremendous risk aversion among hospitals, doctors, insurers. Institutions become deeply wary of this undefined legal exposure, which, ironically, could actually slow down the adoption of genuinely beneficial, potentially life-saving AI tools. The legal system really has to catch up to the speed of generative science before its benefits can be fully and safely realized.
A major hurdle. Okay, and underpinning this entire discussion, the breakthroughs, the hardware, the challenges, is the sheer energy requirement, right? The sustainability imperative.
Oh, absolutely. The immense scale of these new hardware commitments we talked about, like the 10 gigawatts OpenAI is building, or the new Zetascale supercomputers coming online, has really pushed the environmental costs from being, an afterthought to being a central moral imperative.
10 gigawatts is a lot of power.
It's a staggering amount. Data points compiled by our research team confirm that the electricity demand just from global data centers, fueled heavily by this AI adoption wave, could realistically more than double by 2030.
Double the electricity demand in, 5 years? That puts an incredible strain on power grids everywhere. Not to mention the water needed for cooling all these hyperdense racks of specialized silicon.
The numbers are stark. We have to confront them. The training of just one large model, like GPT-4, was estimated to consume something like 300,000 kilowatt hours of electricity.
For one training run.
For one run. Now, multiply that by thousands of models being developed and refined constantly, plus the enormous, continuous energy demand of running inference billions of times a day globally. The strain is simply unsustainable without drastic changes.
Which explains the hardware trends we discussed earlier.
Absolutely. It's why the focus on energy-conscious hardware is no longer just about, saving money on the electricity bill. It's becoming a necessary survival strategy for the industry.
And that's why we see things like neuromorphic computing, these bio-inspired chip architectures gaining strategic importance, because they promise, up to 80% less energy use?
Exactly. And Intel's focus on TCO with Crescent Island is another example. Efficiency isn't just nice to have anymore. It's becoming the primary constraint on future progress.
Right. And this whole confluence of systemic risks, the neurological impact, the legal vacuum, the environmental cost, is that finally driving real action, regulatory momentum?
It seems to be. Governments are definitely shifting gears, moving away from just issuing high-level aspirational principles towards implementing tangible, enforceable rules.
Can you give us some concrete examples of what's happening right now?
Well, the key example our research team flagged this week comes from California. They just enacted some quite targeted legislation aimed specifically at chatbots used by minors and also at managing frontier AI risks.
Okay, what about the chatbots and minors?
They're imposing strict guardrails, things like mandated monitoring for sensitive topics, like expressions of suicidal ideation, with a requirement to immediately provide intervention resources or referrals, and also clear rules requiring the chatbot to explicitly and continuously remind the young user that they are talking to an artificial intelligence, not a real person.
Addressing immediate observable harms, what about the bigger, maybe more catastrophic frontier risks?
That's the second part of the California legislation. New laws there now require the major AI firms, the ones building the most powerful models, to actually publish concrete, verifiable, and importantly audited plans for preventing extreme catastrophic risks.
Like what kind of risks?
Things like measures to prevent the misuse of powerful models, for example, stopping AI from being used to help design bioweapons, or preventing models from exhibiting unpredictable, uncontrollable, run-amok behavior. It signals that regulators are now actively grappling with the possibility of systemic, potentially existential threats, not just localized harms. What's fascinating here is we're seeing the challenges mature right alongside the technology itself. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
Yeah, we really appreciate that.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this whole concept of cognitive debt and maybe what it implies for the future of education.
Definitely want to hear your thoughts on that one. Hashtag text, hashtag outro. Wow, what an immense transformation we've charted this week. Let's try and bring these threads together. Distill the maybe 3 big macro trends that really define this new era of AI unveiling.
Okay, first, I think the overarching theme is definitely specialization over generalization. AI development is, well, it's moving away decisively from that monolithic general-purpose dream. We're seeing highly custom hardware for frontier training, like the OpenAI-Broadcom effort. We're seeing efficiency-focused silicon just for the inference economy, like Intel's chip. And highly specialized foundation models, like that C2S Scale 27B, engineered specifically for niche scientific domains. The future of AI looks, well, purpose-built.
Purpose-built. Okay, trend 1. What's number 2?
Second, the infrastructure race is now, I think, unequivocally the main measure of AI leadership. The sheer scale of these hardware commitments, that 10-gigawatt target from OpenAI is a defining example, demonstrates pretty clearly that leadership is directly tied to securing and controlling multi-gigawatt compute infrastructure. It's become an industrial-scale competition purely for compute resources.
The new space race, maybe. And third,
maturing risk. The scope of AI risk has expanded dramatically. It's moved beyond those early important concerns about algorithmic bias. We are now confronting these quantifiable systemic challenges that are showing up in, well, human cognition itself, in legal accountability for high-stakes decisions, and in the profound environmental sustainability footprint of this incredibly energy-hungry industry. The risks are getting bigger and more complex.
so putting it all together, these developments prove, really beyond any doubt, that AI is capable of accelerating human ingenuity at just an unprecedented pace, solving problems that have resisted human minds for decades, whether that's cracking a cancer puzzle or speeding up material science by 400 times.
Absolutely. The potential upside is enormous,
All right.
but the progress is framed by that paradox we touched on,
Right.
which I think we can't ignore.
The paradox being,
As AI takes on these incredibly difficult challenges outside the human mind, like curing disease, solving intractable physics, are we simultaneously, and perhaps measurably, outsourcing the development of our own core cognitive function? Are we getting smarter collectively while potentially diminishing individually?
that raises a really important question for all of us, doesn't it? What is the ultimate long-term trade-off here for all the speed and convenience? And are we truly prepared to pay the potential cognitive debt accrued by relying so heavily on these increasingly brilliant generative machines?
Yeah, it's the question we need to keep asking. We'll certainly be tracking the answers and many more questions as this future continues to unfold next time on Tomorrow Unveiled.
Thank you for diving deep with us. We'll see you next week.